Let's say an operator notices a rapidly expanding pool of hydraulic fluid collecting below the system. This is quite obviously hydraulic in nature. A hose or connection may have developed a leak, and in a high-pressure hydraulic system, that pinpoint leak could become a dangerous jet of high-pressure fluid. The system needs to be immediately powered down, and the leak needs to be detected. The pool ordinarily collects below the leak, and if not directly below the leak, the path of the leaking fluid should be easily recognizable with a visual inspection. Let's say upon responding to a troubleshooting scenario, you notice an ozone or burned electronic smell upon entering the building. This is electrical in nature. Burned electronics have their own characteristic smell, and you can rest assured that your nose will lead you to this solution. One might notice damaged wires, or one might notice a damaged coil or contact. Let's say the cylinder extends and retracts, but extends very weakly. My first indication that this is hydraulic in nature, since the control aspect of the system is allowing the cylinder to extend and retract. If the cylinder is extending, but extending weakly, my first point of inspection would be the pressure relief valve setting. If the pressure relief valve is set too low or damaged, the cylinder will extend, however will extend weakly. Let's say the cylinder does extend and retract, but does so erratically and noisily. Again, the problem is not electrical in nature, since the control system is allowing the cylinder to extend. My first point of inspection would be the reservoir fluid level. If entrained air is caught in this system, pseudocavitation is occurring, and our actuator would extend erratically and noisily. Additionally, I would check the viscosity and temperature of the fluid to ensure that it is compatible with our system. Let's say the cylinder extends but will not retract. My first point of inspection will be the spring on the single-acting cylinder, or perhaps a jammed piston in the cylinder. Additionally, consider the case where the drill is caught. This system does not have a clamping cylinder, and any workpiece being drilled through might shift in position and jam the piston in the cylinder. We'll discuss later electrically controlled systems that not only incorporate clamp cylinders, but also verify that the workpiece is being clamped. Let's say an operator cannot get the cylinder to extend and the drill will not start. The problem is very clearly inside our control system, since both the cylinder and the drill motor actuate at the behest of the control system. If neither the cylinder extends nor the drill starts, my first point of inspection will be the common control system. If, however, the cylinder did not extend, yet the drill started to rotate, I would inspect the second rung of our ladder logic control system, or I would check our hydraulic power unit. Solenoid-operated valves typically have a pilot light associated with the solenoid, which allow an operator or technician to verify if the solenoid is being energized. Additionally, the valve being a physical device that shifts position, one should be able to hear or feel movement. The relays themselves are again physical devices. One should be able to see the coil being energized, and when the coil is energized, those associated contacts should change to their opposite states. Pressure, flow, voltage, and current ratings at various points within our system should be able to identify the source of our problems. Another great technique for practicing troubleshooting scenarios is to mentally insert an error into our system. If you really understand this system, you should be able to predict how the system will react. Consider a broken wire in the second rung of our ladder logic diagram. If both push button 1 and push button 2 are simultaneously closed, control relay CR1 would energize and the associated contacts would change state. However, the broken wire in the second rung of the ladder logic diagram would not allow DCV1 solenoid A to energize, yet the third rung would allow the drill motor to rotate. In this case, the drill would rotate, but the cylinder would not extend. Consider loss of the L2 phase in the three-phase power supply. If push button 1 and push button 2 were simultaneously closed, the cylinder would extend, yet with a loss of one of the phases inside of a three-phase AC power system, the three-phase AC motor would have difficulty starting. Before we close out troubleshooting, consider the intended function of this system. An electrically controlled system does what it has been designed to do, and if you design a machine to destroy itself or drill a hole through your hand, it will do so without a moment of hesitation. Electrically controlled systems are again not self-thinking machines and merely act out the instruction set inside the programmable logic written by the user or hardwired into the relay-based ladder logic. Consider an operator simply so tired of keeping both hands on push button 1 and push button 2 while the cylinder extends, and so desperately longing to take a smoke break. The operator takes it upon themselves to attach a low resistance wire in parallel to push button 2, effectively making push button 1 the sole input in charge of extending the cylinder. As if that wasn't enough, the operator takes another jumper wire and bypasses the normally open contact CR1B, effectively keeping the drill constantly spinning. This operator, by modifying the hardwire connections, has effectively modified the behavior of the system with potentially disastrous consequences. It's only a matter of time before this injudiciously modified system damages itself, valuable raw materials, or mangles the operator it was intended to protect. This is to again suggest that machines do not think, but only act. You can always trick a machine by jumping a switch or forcing a desired output, but it may not be the wisest or safest course of action to do so. Alright, that's about it for this brief introductory discussion on electrically controlled systems. A housekeeping note before we close up shop. This introductory lecture on electrically controlled systems is meant to service both the hydraulics and electrical control of hydraulic systems playlist, as well as the complete electrical control playlist. If your interest is exclusively in electrically controlled hydraulic systems, realize you'll be leapfrogging a tar pit of pertinent electrical background and dealing exclusively with the hydraulic aspects of electrically controlled systems. One might think the electrical and hydraulic aspects of a system are totally independent of each other, but one needn't look further than the pump central to the operation of most hydraulic systems to find an example of a hydraulic system that requires knowledge of motors and contactors. This brief step into the tar pit having been complete, let's fully immerse ourselves and begin thrashing. How are we going to protect the motor-driven pump from sustained overload conditions? The answer is with an overload device. What's an overload device and how does it work? The answer is it's part of a motor starter, being the means of starting and stopping a motor and protecting it from sustained overload conditions. We are now hopelessly mired in the tar pit, and any further thrashing will only serve us to get further entangled. It is for this reason that the hydraulics and electrical control of hydraulic systems playlist largely separates the electrical and hydraulic aspects of systems, and most examples use 24-volt DC control voltages. Do not for a moment assume that this is always the case. There are solenoid-operated valves and control relays that run on 24 volts AC and 120 volts AC, among other magnitudes and flavors, and sometimes electrically controlled hydraulic systems need to start a motor-driven pump. The only reason I'm purposely dividing the subject material in this manner is that the prerequisites of basic DC electronics and basic hydraulics are very low hurdles to clear. These hurdles having been cleared, one can gain an early exposure to electrically controlled systems. As one further develops electronic skills to include single-phase AC circuit analysis and three-phase AC circuit analysis, those base skills can be brought into the larger picture as we progress into the full electronically controlled systems playlist. It really is all connected, but one can't make connections by thrashing around blindly in the tar pits. If you follow the path I've laid out for you, you'll progressively make more and more connections with more and more material. If you stay in your lane, you should feel comfortable with those targets inside your lane. If you want to look outside your lane, that's okay too. The first part of the electrically controlled systems playlist is this lecture, which serves as the briefest of brief introductions to the topic. The next several lectures introduce key cast members of the electrically controlled systems family, principally the solenoid-operated valve, the principal interaction point between the electrical pilot and primary hydraulic aspects of an electrically controlled hydraulic system, the contactor, the principal interaction point between the pilot and primary electrical aspects of an electrical controlled system using motors, The overload, a means of protecting a motor from sustained overload conditions. The motor starter, being a combination of a contactor and overload, serving as a means of simultaneously starting and stopping a motor and protecting it from sustained overload conditions. The control relay, the principal logical element internal to an electrically controlled system. Additionally, we'll review basic circuit protection devices like fuses and circuit breakers, and take a closer look at some typical manual and mechanical or automatic switches used as inputs to an electrically controlled system. If you've got time to do so, I'd recommend maybe revisiting the circuit protection and switches lecture from way back in the Basic Electronics 1 DC Circuit Analysis playlist prior to moving on to these lectures. It may help to refresh the hardware-specific aspects and functionality of these devices as applied to basic circuits and review common terminology before moving on to the specifics of these lectures. Once we get a good look at these devices, we'll move right into incorporating these devices into increasingly complicated electrically controlled system applications that can start, stop, change direction, modify operating characteristics, time, count, sequence, compare, communicate, and more using ladder logic. Systems of unimaginable complexity can be constructed using switches, sensors, programs, and outputs. Closed-loop control of actuator position, force, and speed can be achieved with amazing precision and accuracy at speeds surpassing human perception. I must remind you, though, machines do what they have been told to do. If inputs report false data, if the internal logic is somehow flawed, or if the outputs somehow malfunction, the system won't work as intended, and those unintended results could have grievous consequences for the industrial process the machine controls and those individuals that rely upon the proper functionality of this machine. In conclusion, this lecture took an introductory look at electrically controlled systems. We identified the primary purposes of electrically controlled system, differentiated between the control or pilot and the power or primary inputs, and differentiated between switches and sensors. Additionally, we briefly introduced the contactor, the principal interaction point between the pilot and primary aspects of an electrically controlled system incorporating motors, the solenoid operated directional control valve, the principal interaction point between the pilot and primary aspects of an electrically controlled system incorporating fluid power devices, and control relays, the principal logical element of an electrically controlled system. Additionally, we introduced programmable logic controller, which is largely replacing hardwired relay-based ladder logic, but interestingly enough, is still programmed using symbols and techniques largely identical to relay-based ladder logic. The principal difference between these two different methodologies being that hardwire relay-based ladder logic must be physically rewired to change the functionality, whereas PLC-based systems can be simply reprogrammed to change the functionality of the system. We discussed the logical AND operator, the logical OR operator, and had a brief discussion about troubleshooting electrically controlled systems. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.